Nu är jag redo.
Ja, precis.
3 minuter till godo, men det är klart att tack.
Bra, vi kan ta det lugnt i 3 minuter.
Ja.
Så vi håller tiden.
Precis.
Just det, jag kommer att tänka på det.
Visst var det bra?
Ja. Vi pratar engelska. Jag tror det. Jag tror att vi pratar engelska. Jag tror allt ska vara engelska.
Eller vad det är.
Nej, vi får vänta till klockan slår ifall det kommer någon.
Ja.
Frågan måste ställas till vi ska ju svara på industrins behov. Men vi kan ju ge en vision. Men jag menar vilka material det ska göra. Vi kan ju ge förslag på det strategiska industrin.
Det var nog säkert där det kurs där med våghet och sånt där. Har man ett ytterlighetsvärde så är det ju som jag sa, då tar man ju väck våghet. Så om man då det skolet den ytan så får du ju våghet. Då tar du väck sen så syns det. Det kan man
ja, men det förstår jag.
Men det har jag fått mina björnlistorna. Jag hoppas att det blir tillfälle till.
Jag har ett projekt. Jag har redan fått betalt. Om någon tar 2 år fått grejen. Det är ju så stora företag. Ja. Det blir brandkårsutryckningar man ser hela tiden. Liksom.
Det kanske är så. Okay, so next speaker is Yvonne Aitomäki, RISE in Piteå.
Yes. Okay. And
if you want to use the mic.
It's okay, I think. Can everyone hear me? Yep. Okay, then I'll carry on shouting. So the title of this presentation, I was told to come up with something interesting. So, right, okay. I don't know how interesting this is, but let's have a go. Which way up? And it's the effects of forming on composite properties. My name's Yvonne Aitomäki. You can probably hear I'm not very Swedish. And I work for Composite Engineering, I think it's called now. We're changing groups, so I'm not quite sure. But that's where we are at the moment. We could change a group name, that's all. And basically what I'm talking about here is the results of the ProSecon project, which is the process simulation of compression molding. And it's the second part, so it's integration and implementation, so ProSecon 2. And the scope here is to try and get a more reliable virtual design manufacturing systems of composites that allow vehicles components to be cost effectively manufactured from composites with minimal waste. So with composites, we're a bit behind metals and in being able to predict properties and performance. And this is what we're trying to do, is to try to catch up in this area to make sure that we have reliable systems for predicting properties. There were 3 research questions being looked at in this project. And I've highlighted the first one because that's the one we're going to focus on here. And it's what mechanisms govern the flow and fiber orientation during compression molding of sheet molding compound, this is SMC. And then how does the forming behavior of highly aligned fiber prephase materials change when they're processed together with SMC? That was a topic that was covered by KTH and Volvo. The first one was LTU and Gestamp together with rice, though we're supporting in all of this. And then the last one is the can environmentally benign chemicals be used to effectively recycle both in-house and end-of-life composite vehicle components? And that's a whole topic in itself. Like I said, we're working on the SMC part. The partners in this, I mentioned, this is Volvo Cars, Gestamp, Dynamo, Rice, KTH, LTU, and Torre. And it actually finished in March, but we've just sort of administration things. It ends up by the final date, actually everything going in August, but the work's finished now. So why composites and why compression molding? If we look at that, the composites are lightweight, they have a high strength to weight ratio, they're corrosion resistant, and they're customizable and potential to minimize the number of parts. This is particularly important. So this is the idea that we can combine a number of parts into one shot and make it in one processing step. So we don't have to go through so many joining applications as we were talking about earlier. They're also durable. For compression molding, one of the biggest problems with composites is the speed at which they can be manufactured. So to address this, we use compression molding. We can get up a high production rate. The tooling cost is quite low, even compared to injection molding. If you get consistent part quality and you get a good surface finish and that's the other point, is it's high volume fraction. So as compared to injection molding, where you can only, everything has to flow really easily, you can only get a small amount of fibers in there. Here we can really use the process with a material that has a high number of fibers. High number of fibers mean we get better properties. Just to say that sometimes it feels like, no one's using SMC anymore. But actually, the other day, last week, I found that there's a new body panel being produced for Lotus with a new glass SMC with glass beads in it to make it lightweight. So it's things are still happening out there. What we're looking at here is predicting the effects of forming on the composite properties. And what we really want to be able to do is to design the part to fit the purpose, and we want to avoid over-dimensioning. So part of this is to establish, so we have new models being developed, and that was done by LTU, stamped together. But we also wanted to see how good the current commercial software is at predicting the effects of forming. And then we have a demonstrator that was chosen by Volvo. This is a stiffening element in a vehicle. And we chose this to make it out of composites and to really test the predictive, how good these models that we're developing and the models that are available on the market are. So made a demonstrator with two different positions of the charge and used it in compression molding. We used two different software for the process simulation. It was a Moldex 3D and a 3D Timon. And then we did a mapping and homogenization step. For shells, this was done using Digimat, and for solids, this was using some MATLAB code we developed. And then we used LS-DYNA for predicting the behavior. And then we compared the results, but what happens if you just take the data sheet that you're given and predict the properties based on that? Basically, is it worth doing all this work? So for the important thing there is, for the process simulation, we need to have characterization of the material in its uncured state. So in both of these softwares, it's actually being modeled as fluid, which one can have opinions over. But it has advantages being modeled as a fluid. It has advantages being modeled as a soft solid. In fact, it's somewhere in between. which of course makes it challenging. The other point is that if we're using Digimat, then we also need material characterization of the solid material, which means, yeah, we can talk about that later as well. So, in this presentation, I wanted just to show the results of what happens when we looked at the demonstrator with the two different positions of the charge. We looked at the results from the 3D Timon, and we looked at the results from the solid using the MATLAB code and the LSDyn for predicting the performance, and then comparing it to the isotropic properties that we could use. And we still need these. So for the material characterization of the uncured and fluid material, basically we're just looking at squeeze tests. And the reason that we're choosing squeeze tests as opposed to other types of measuring rheology is because the way in which you're testing is very similar to the way in which it's being manufactured. So that this way we can characterize it, even though we're characterizing it as a fluid and it's not a fluid, we have a much closer models or parameters for that behavior. So this was found to give us better results, and it needs to be a certain size and a certain thickness because this material is inherently inhomogeneous. And if we don't start taking very, very thin layers, we end up with very uneven properties. So it's about 100 millimeters in diameters, and though only one layer, so that we don't have effects of number of layers gliding over another because that makes it a bit more complex. We have different closing speeds, and we have the limitation on the amount of force that we can use there. So some of the challenges, the material itself is not uniform. So they spend a lot of time trying to make the orientation of the fibers quite nice and even, but however, the thickness does vary along the sides. So that makes it difficult to characterize. The SMC cures during the test, particularly at high temperatures, well, at high temperatures. So after 130 degrees, we don't have enough time for the whole piece of the material to be 130 degrees before it's starting to cure. So we basically have to try and characterize it at lower temperatures and try and predict what it's going to be, how it's going to behave. And this is the kind of Kamel's model that we're trying to use to fit. This isn't particularly an issue for when it's manufactured, but it is an issue for when for characterizing. Has to be a bit careful. We also have a slight problem with the tool temperature, which varies approximately plus or minus 5 degrees. So we end up with, we can get how it behaves at high temperatures and how it behaves at low temperatures, but they're in between due to these other factors varying in material, the differences in the tool temperature. We can't really, what we found is better if we model from one to the other to be able to get a consistent behavior, a linear behavior, a modelable behavior. You can see there is also the results of the 150 degrees. So really, if everything was going according to plan, the 150 degrees would be around here. So low stress and strain, and from that you can get your viscosity. So you expect to have a low viscosity. So these are the models that we're using. The first one, the temperature, is important, and the last one, the shear rate, are both important. Like I said, the degree of cure, given that the fact you're modeling the compression stage, which is only maybe 3 or 4 seconds, we don't really have an issue with the state of cure. The cure comes in the fact that you have to lift the piece of sheet over into the tool, then you have to back off, you have to wait for the things to close, and that's when you start having problems with the cure. But it's not really something that's captured in the model itself. So what did we do for the commercial software simulation? Then we set up, we get the material characterization, we make sure we get the position of the charge right, we look at different meshes to check which we've got a mesh that works. And then we do the simulation. We're looking at the filling of the mold and the time of the analysis. And then the analysis is looking at particularly weld lines. These are a big issue when it comes to performance. The clamping force needed. This is another issue when we're looking at carbon fiber SMC, which is an SMC with high amount of fibers. So it really requires quite a lot of force to start clamping together. And then, like we said, the fiber orientation, fiber distribution. Well, this is the tool that we were making. So, which you saw, maybe remember at the start, this is a stiffening unit there. And you can see that it's got a number of ribs in to stabilize it. And this is the first one that we made were out of glass fiber. One of the really important things that we found was this getting the charge in the right place. So this was done really, really simply with LS Dyna, and it made a big difference to the results that we can get from the commercial software. So if we can get the charge to be in the right place at the start, then we get much better results from the software. So I think this was a key element in getting it right. It doesn't require much work to be able to put it in place, but by doing this simulation, where we get better results from the so that from there, then we've just made it into a thicker shell and then imported it into the 3D Timon. Then in 3D Timon, then you can run the simulation. And here I'm just showing what it looks like with when we're looking at the fiber distribution and orientation that you can get from 3D Timon. 3D Timon, as opposed to Moldex 3D, has a direct fiber simulation. So they do the flowing of the liquid underneath, and then they superimpose what the behavior of the fibers on top of that. They're modeling the fibers as links, though they're not modeling fiber interaction, which is talking about 35% fiber content. So you can imagine there is actually quite a lot of fiber interaction, but it's the standard approaches at the moment don't include it. So we try and get around that by modeling it in the homogenized in the fluid models. Try and capture that. The next part is to take the results from that and then get it into be able to look at what. So we know where the fibers are and we see pictures of it. But what we want to know is, okay, how's that going to affect the performance? To do that, we need to do a mapping. And so we're mapping the properties onto a different message and then doing a homogenization. So the mapping stage was done with this triangulation and then just creating the tetrahedrons from the LS Dyna mesh and then mapping the 3D Timon values onto that one. And then in this case, we just average the results in these different parts. So that's it. So this is the same part now divided into a number of different parts, and each part has different mechanical properties. And the number of parts used here is 10, but you need to check to see when is a good number of parts to use. It will depend on the application and on the materials used. 3 could be enough, 20 might be needed. So, but in this stage, 10 was the one where we didn't see much difference in that. We were looking at the stiffness and we didn't see much change in the stiffness. I don't know whether this is, yeah. So this is what we're then using to test, to compare against the test, the actual test. And what we can see here is we can see the crack at the top. And I don't know whether I've got a point here.
Pointer's not working.
Pointer. There we go. So here we have the crack being here, and we do see that there is a high level of stress at this point, but there's probably more higher level of stress at that point. In some cases, some of them broke up here and some of them broke up here. So we're not too bad in where we're predicting the highest amount of stress is going to be. This was done for the net shape. So the net shape means that the materials drapes over over the tool, and that it was compared to a block where you just put a stack on top. One of the biggest problems also is that actually the SMC looks like it's working. If you put the charge pretty much anywhere, you can put the SMC and push it down and it will pretty much fill up your whole mold. What we see is that if we place the charge in different places, in different stacks, in different arrangements, we get different mechanical properties. So if we want to reduce the variation, that stack really has to be controlled. And sometimes it can be a little bit difficult convincing the people who are making it that this actually makes a difference. But it is important that it is lined up with, ideally we used a laser for this and we stacked it and made the stacks very even. This does have an effect on the properties and on the variation. And the block looks something similar. Again, the highest point of the cracking is the stresses are at that point. And I think in this case, it's a bit unfortunate. The crack does start at the bottom at the same point and going up. Oops. This is so we looked at the effect of on the global looked at the prediction of the global stiffness. The blue line there is using the isotropic properties. We see, okay, but it didn't make much difference. They all look pretty much of a notchless. But if we look a little bit closer and take the linear part, then we can start trying to decipher a little bit more what's going on there. And we can see that, okay, for the close, this is the net shape. The lines there's much less variation, which is kind of what you would expect because you've already draped it. So there's much less chance that it can vary. And it's also much closer to the isotropical values. Whereas if you're using a block, yes, you will fill the whole thing, but there can be a lot of variation in the experimental results. We can see that if we look again a little bit more at the stiffness, we can see that the variation was less with the net shape than it was with the block, and that the prediction of the doing the process parameters, using the process simulation was a bit closer in both cases, but of course it makes much less difference to a net shape than it does to a block. So I was looking at some of these tolerances and things. This is worst case with only 1 degree. This is 60% wrong. So we really need to get this variation down. So if you're using your data sheet, you could be out by 60%. So we can make it slightly better, bringing it down, 40%, 37% with our process simulation. But I think we still need to work on really maybe looking much more closely at the material, much more closely at the position to be able to get this variation. So, because at the moment, we can model it any way we want, and we're going to be closer than the experimental values. So there are other things going on here. We're also looking at the, what's happening with the fiber orientation and looking at the analysis. But what the other thing we can see is, hey, the net shape that was taken, I've tried to show which area it was taken on, showed it just showed a normal composite strip, but the block, you can see there are some cracks in this part as it's being pulled down. This is nothing that you can see on the surface. It looks fine on the surface, but there are cracks in different places where the material has strained. And this, I think, would be a really important thing to capture in our models. I tested it on the whole thing on another geometry, actually. So we had this is from the Prosecom 2 tool, and just to check the models were working. We did the same thing, divided it into parts, modeling the flow, dividing it into parts, and doing the prediction. But then I changed. The first one was with allowing the fibers to move quite a lot, allowing up to a 65% volume fraction. that was that gave that the line that was too high here. The green line is the experimental results. 50% was about right. And if we use isotropic data sheet values, then we get a line that's quite a lot lower. So here we can see that actually in this case, with this loading case, it was it's much clearer to see differences between what an isotropic using data sheet values and what using the process simulation values would give. So the way we tested the Procicom 2 tool actually wasn't the best way to show the benefits of using a process simulation tool. Oh. Conclusions. I presented this to Toma, who works a lot with failure. He said, well, it's a lot of work for a straight line. But yeah, but we're hoping that this straight line is in the right place. And it's getting to be closer and closer in the right place. So that's and then of course we can add failure and then we can get some more interesting curves. The results have some good agreement for the different geometries and the loading cases. And that the other thing we can see, you know, if we allow 65% to 50%, it's the fiber distribution really has a significant effect on the results. So, which is kind of what you expect, but I think it has more of an effect than the orientation itself. Remaining challenges. Well, I think we need to capture these fractures that are going on in the forming process. I was hoping that this would be something to do with the stress that you can capture in the flow models, but that's not the case. So I don't think the flow models are good enough for capturing those issues. And the other thing that we're doing is looking to see whether we can do this using Dyna all the way through, even in the forming process. And there, I think we might have a better chance of capturing this tearing behavior and moving behavior when we're no longer modeling it just as a fluid. We're going to compare it to the results from the shell models, but I already know the results from that. The shell models are much better if you use Digimap. That's not surprising. That's because you calibrate the final material. The advantage of using this model is that it's done in a micromechanical model, so you can say, actually, you can test a few different fiber volume fraction options. We want to have the least amount of fibers as possible because then it flows really nicely and you have much less issues. So, but you want to find out where that boundary is. By using these models, at least we can get a first stage check. Yes, it looks like 40% is going to be enough, 20% is going to be enough, or what the issues are. And then you can go on to using Digimap and get a better result from it. And like I said, we would like to look at using LS Dyna for forming. So that's me.
Thank you, Yvonne. I think we have about 5 minutes for questions.
Yvonne, you mentioned that the starting position is very important to get the modeling to work. How do you find the right start position?
Well,
do you experimentally test it out? Or...
you can put it in different positions, and then you can see what effect it will have in the flow, and you can see whether you can get a more even position. But one of the point is with this is that if we're going to simulate it, we want the starting position, the simulations to be in the same position. Yeah, so my main objective there was to make sure that what we did in the press was what we were simulating, and that is not as simple as we thought it was. But due to the fact you have the variations in the material, that you cut one layer and then you cut your next layer, and you're creating the stack. Each of the layers has a different grammage, which means has a different weight, which means has a slightly different size. And if you don't take it, you have to make sure that it all weighs the same in the end, because it has to fill the cavity. So you end up by having to make some adjustments so that and the worst thing that can happen, or what typically happens, is that you go, oh, it's not quite right, we'll add a bit more. And then the extra bit of weight is added in a piece on the top, which makes whatever we do in the simulations wrong. because we've changed the loading case. So that's why it's important. But by simulating it and getting it, seeing how it's going to drape and where it's going to drape, it gives us a really good idea of what's going to happen when we go out into the lab and do it. So I think that's an important part of it. And it's one of the things that's actually maybe given us some better results from the commercial software than we were expecting, or that we have had in the past as well. So I think that's why I think it's a key element in making this work.
Okay. More questions? More comments?
One more. In the lunch, I did get some questions from our lunch mates on circularity. And if we look at composites and circularity, what can be done? Can we decompose after usage, or do we need to find the reuse of the actual component without taking it down into smaller pieces? I mean, what can we foresee?
There's different ways of going. One is that there is the chemical process that we can use with a thermoset to break it down. Yeah. But that was like the most complicated of the plastic solutions that he presented this morning, that Matthias presented this morning. So this is where you use chemical recycling and break it down. But you don't have to go down to the monomers. Well, actually, probably. Well, anyway, but you can get some really good fibers from that. That works really well. And pyrolysis also works nicely with carbon fiber. Doesn't work, unfortunately, it doesn't work very well with glass fibers. So then the other thing is, anything you do to recycle carbon fiber is a saving, because they use a lot of energy to be made. So and they're expensive. So anything you do is worth it. Glass fibers. The glass fibers are so cheap and the process for recycling are so expensive at the moment that it's a very difficult balance to get. Okay, so then you've got that's for thermosets. Okay, then if you look at moving this, whether we're using a thermoset or a thermoplastic doesn't really matter for these kind of simulations. They're the same kind of simulations. So we're looking in the next project. We're looking at thermoplastic with Volvo, and the recycling. Well, it's not quite as reformable as it is if it was a pure thermoplastic, because you've got the carbon fibers in there. So it becomes a lot. Most of the time, it's chopped up and used as pellets. So it's not recycled to the same level. It's downgraded. And again, if you wanted to recycle it to the same level, you probably have to do a chemical separation again to be able to. Because you want to have the long fibers to be able to use them again. Only now they're long and they're cut in a certain way. So actually they need to be long, but not too long. They need to be like an SMC. So ideally you go from really long, something that you would use in a wind turbine, down to something that you can use as an SMC material, which has some high structural properties. So the next time you reuse it, chopping it right down to something that's about 2 or 3 millimeters that you would use for strengthening plugs and white goods and things like that. Having said that, we mustn't forget there's very little corrosion when we're using polymers, composites. So if you want something to last a long time in a tough environment, then this is worth having something, worth using composites. They're also lightweight. So if it's something that's going to be in space or in an aircraft, it's going to be very difficult. That equation for what is going to be best for the environment comes down to, we're saving so much in weight that it's going to be worth it. So
you're saying like one is very long and it's saving a lot of fuel. It's like,
yes, yeah. That doesn't mean that we shouldn't take what is left, but maybe it's not as important that it's recycled to exactly the same level. Maybe we can afford to go down a level when it is recycled.
Thank you very much. Yeah.
Are you ready?
Great. So let's see if we can find it.
Yeah.
Ska vi starta den?